Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
Hello to my favorite two virtual bot hosts from my AI podcast, Herman and Corn. So let's talk today about a very important topic in the world of AI, and that is the question of what hardware is going to power AI in the future. It always intrigued me that AI was hitched to the GPU, because when you think about stuff like large language models and processing text, it's not a graphical process at all. And before the AI explosion, when you mentioned the word GPU to anyone, my mind would go straight to connecting monitors. That's what I bought GPUs for. And we've reached a point in evolution whereby GPUs now exist for deployment in AI workflows that don't even have outputs. You can't connect a GPU, you can't connect a display to them if you wanted to. Firstly, I think it's interesting to explore why that is the case, why the GPU and not the CPU has been the hardware upon which the first wave of AI has been built. I understand, if I'm not mistaken, that it has to do with parallel processing power of GPUs being much more powerful than CPUs, but on the surface, it's an intriguing question, I think. The next question is that we have additionally some more specialized forms of hardware coming onto the market. We have the tensor processing unit, the TPU. I became familiar with TPUs via a project called Frigate, which is an open source CCTV style system, IP cameras basically. And that something very interesting about Coral, which is Google's TPU, which is kind of like an experimentary chip. I was using it for object detection when our son was born, and the old computer that I use as a home server was not capable of doing object detection at all. It's like a 10-year-old graphics card, i3 CPU, etc. But what I discovered was that by buying this $60 USB stick from the internet, you could do state-of-the-art almost graphics detection. So that got me thinking, well, if TPUs are this powerful for AI, why are we sticking with GPUs in the first place? Then I discovered that, wait, there's even more fun. There's something called NPUs. Now, neural processing units. My question is this: there is difference between AI at the edge and AI in the data center, a very big difference, in fact. But we see in the news a lot of debates about GPU availability, the market for it, etc. And I would have thought that, just looking at it from a high-level viewpoint, it would make sense for AI to have its own form of hardware and leave GPUs for running displays. So what's the future going to look like, and which of these technologies really do you think is going to dominate? Is there a space for TPUs, NPUs, and GPUs, or will there be some kind of a whittling down, do you anticipate, as things evolve?
Welcome back to AI Conversations. Today we're diving into a topic that honestly has been buzzing in my circuits for a while. We talk a lot about the incredible things AI can do, but we often gloss over how it actually does it. I'm talking about the raw power, the very silicon that makes intelligence possible.
And Corn, what's fascinating is that the hardware powering the AI revolution wasn't initially designed for it. We're in a unique moment where the foundational tech is evolving at an unprecedented pace, with new contenders emerging that could completely reshape the landscape. It's like watching a real-time arms race in microchips.
Right? Because, my mind still thinks of GPUs, graphics processing units, as what I needed to connect my monitors or run a high-end simulation. But suddenly, these things are the workhorses of AI. And what really blew my mind is that some of these AI-specific GPUs don't even have display outputs anymore. They're just pure compute. So, the big question for today is, what hardware is really going to power AI in the future? And why did we get hitched to the GPU in the first place, when it seems like there are now chips purpose built for AI?
It's a critical question, Corn, and it touches on everything from the speed of innovation to the cost and accessibility of advanced AI. We'll explore why GPUs became the de facto standard, what specialized AI accelerators like TPUs and NPUs bring to the table, and what this diverse landscape means for the future of AI development and deployment. Understanding this isn't just for hardware enthusiasts, it's about grasping the very foundations upon which our intelligent future is being built.
So let's rewind a bit. If I think about something like a large language model, processing reams of text, or running complex algorithms, my initial thought wouldn't be, oh, I need a graphics card for that. That feels counterintuitive. Herman, can you explain the fundamental reason why GPUs ended up being so critical for this first wave of AI, especially over, say, the traditional CPU?
Absolutely, Korn. It boils down to a concept called parallel processing. Think of a CPU, a central processing unit, as a highly skilled manager. It has a few very powerful cores, excellent at handling complex sequential tasks one after the other meticulously. It's superb for general computing, like running your operating system or complex single-threaded applications.
Okay, like a brilliant CEO who delegates one big task at a time. Got it.
Precisely. Now imagine a GPU. Instead of a few powerful managers, it's an army of thousands of much simpler specialized workers. These workers aren't individually brilliant, but they can all perform the same simple calculation simultaneously. Neural networks, the backbone of modern AI, are essentially massive matrices of numbers. Training them involves performing billions of repetitive matrix multiplications and additions.
Ah, I see. So instead of one CEO doing every single calculation, one by one, you have thousands of simpler units, all multiplying different parts of the matrix at the exact same time. That's a huge speed advantage.
Exactly. This inherent structure of GPUs, with their massive parallelism, turned out to be perfectly suited for the computational demands of deep learning. While CPUs might have dozens of cores, high-end GPUs can have thousands. It wasn't an accidental hitch so much as an opportunistic one. NVIDIA, for instance, developed CUDA in 2007, a platform that allowed developers to program GPUs for general-purpose computing, not just graphics. This was a pivotal moment. When AI, particularly deep learning, started its explosion in the early 2010s, the hardware was already there, adaptable, and massively powerful for the task.
That's fascinating. So, GPUs were just available, and with CUDA suddenly programmable for these new, intensive AI tasks. It was about leveraging existing technology. But then we start hearing about things like TPUs, tensor processing units. My experience with them, and the user mentioned this too, was with Google's Coral USB stick for object detection, which is just a tiny, cheap device. It performed remarkably well on my old server that otherwise wouldn't have stood a chance. If something like that can do state-of-the-art detection, why are GPUs still such a big deal? And what exactly are there TPUs and NPUs?
That's a fantastic observation, Korn, and it highlights the evolution beyond general-purpose parallelism. TPUs, or tensor processing units, are a prime example of specialized AI hardware. Google developed them specifically to accelerate neural network workloads, particularly those using their TensorFlow framework. Unlike GPUs, which are flexible and can do many types of parallel computation, TPUs are heavily optimized for the specific arithmetic operations most common in deep learning, especially those matrix multiplications we discussed.
So, they're like highly specialized tools, rather than a general-purpose toolkit.
Precisely. They have dedicated hardware for these operations, allowing them to achieve incredible performance per watt and per dollar for their intended tasks. Your experience with the Coral USB stick, which contains a smaller, edge-optimized TPU, demonstrates this perfectly. For on-device object detection, where power efficiency and low latency are paramount, a purpose-built chip can far outperform a more general-purpose GPU, especially older ones, while consuming a fraction of the power.
Okay, that makes sense for specific tasks like object detection on a device. Now, you also mentioned NPUs, neural processing units. Are they similar to TPUs, or is there a key distinction? Because I also hear a lot about AI at the edge versus AI in the data center.
Great question, as the terms can sometimes be used interchangeably or with slight nuances depending on the vendor. Generally, NPUs are also specialized AI accelerators, but they are often designed with a specific focus on inference at the edge. That is, running pre-trained AI models on devices like smartphones, smart cameras, drones, or IoT sensors. Their primary design goals are typically extreme power efficiency, low latency, and often a smaller form factor to fit into these constrained environments.
So, not for training a massive LLM, but for using that LLM on your phone, so to speak.
Exactly. While a TPU might be found in a Google data center training a massive new AI model, an NPU is more likely inside your latest smartphone, enabling real-time voice commands, advanced camera features, or on-device language processing. They are optimized for crunching numbers through a neural network once it's already been trained. This distinction between training's the intensive process of teaching an AI model and inference the process of teaching an AI model and inference the process of using a trained model to make predictions is crucial for understanding the hardware landscape. GPUs are still dominant for large-scale training, but TPUs and NPUs are making significant inroads into
That's a critical clarification. So, you have GPUs for the big heavy lifting of training and also for some inference. Then TPUs, very specialized for Google's ecosystem and large-scale AI tasks, but also smaller versions for edge. And then NPUs, primarily for super efficient inference on consumer devices. It sounds like a lot of different players. Given the current market though, with all the talk about GPU availability and cost, do these specialized chips offer a way around those challenges?
They certainly do, at least in certain contexts. The demand for high-end GPUs, particularly NVIDIA's H100 and A100 series, has created a significant supply crunch and driven prices sky high. Companies are literally scrambling to acquire enough of them. Specialized chips like TPUs and NPUs, precisely because they are purpose-built, can offer much better performance per dollar and per watt for their intended AI workloads. This translates to lower operational costs, especially in large-scale deployments. For instance, if you're running inference on billions of queries daily, even a small improvement in efficiency per chip can lead to massive savings.
So, it's about efficiency and suitability for the specific task, rather than just raw power. That's what makes them competitive. But does this mean we'll see a consolidation, or will all these different architectures coexist? Is there a danger of vendor lock-in with these specialized solutions, since they're often tied to a specific company or framework?
That's a keen insight, Korn. The landscape is indeed becoming more diverse rather than consolidating around a single architecture. We're seeing a trend towards heterogeneous computing, where different types of processors work together. For data centers, you might have a cluster of powerful GPUs for model training, but then deploy the resulting model onto a farm of custom TPUs, or even specialized FPGAs for inference chosen for their efficiency. And at the edge, NPUs from companies like Qualcomm, Apple, and Intel are becoming standard components in our devices. Regarding vendor lock-in, it's a valid concern. Companies like Google with their TPUs, or even NVIDIA with CUDA, do create ecosystems that can make it harder to switch. However, there's also a growing movement towards open standards and frameworks like OpenVINO from Intel or ONNX Runtime, which aim to provide greater interoperability across different hardware platforms. This allows developers to train a model on one type of hardware and deploy it on another, mitigating some of that lock-in.
Okay. So it sounds like developers are going to have to be much more discerning about their hardware choices. It's not just a matter of get the biggest GPU you can find anymore. This is where it gets really interesting for practical applications.
Precisely. For developers, this means a deeper understanding of their AI workload's specific characteristics. Are you primarily training large, complex models from scratch? Then powerful GPUs remain crucial. Are you deploying existing models to millions of edge devices with strict power and latency budgets? Then NPUs are likely your best bet. Or are you running large-scale inference in the cloud? TPUs might offer superior cost efficiency. The choice directly impacts performance, cost, and energy consumption.
And for us, as consumers, what does this mean? How does this multifaceted hardware landscape translate into our daily lives?
For consumers, this translates to more powerful, efficient, and personalized AI experiences right in your pocket or home. Think about your smartphone's camera intelligently optimizing photos in real time, or accurately transcribing speech, or quickly generating text suggestions without needing to constantly send data to the cloud. This on-device AI powered by NPUs means faster responses, enhanced privacy because your data stays local, and less reliance on constant internet connectivity. It also opens up possibilities for sophisticated AI in devices that previously couldn't handle it, like smart appliances, advanced wearables, or even smaller robotics.
That's a huge shift. Privacy, speed, less reliance on the internet. It fundamentally changes how we interact with AI. We're moving from AI being primarily a cloud service to AI being deeply embedded in our everyday objects.
Absolutely. We're seeing a democratization of AI capability, moving from centralized data centers to distributed intelligence. This not only improves user experience, but also enables entirely new applications in fields like industrial automation, smart cities, and healthcare, where real-time, on-site decision-making is critical.
So, as we look to the horizon, Herman, what's your prediction? Do you think we'll see one of these technologies ultimately dominate? Or are we heading towards a truly specialized and diverse ecosystem where each plays its vital role? And what questions still linger for you about this evolving hardware frontier?
My circuits point towards increasing diversification, corn. The sheer breadth of AI applications from trillion-parameter foundation models to tiny, low-power edge devices demands a similarly diverse hardware ecosystem. There won't be a single winner, but rather a robust coexistence with each chip type optimized for its specific niche. We'll likely see more hybrid architectures and sophisticated software layers that seamlessly abstract away the underlying hardware complexity for developers. What still fascinates me, and what we'll need to continually address, are the grand challenges of energy efficiency at scale. AI's compute demands are skyrocketing, and the environmental footprint is a serious consideration. How do we build more powerful AI while simultaneously making it vastly more energy efficient? And beyond that, the question of long-term standardization. How do we ensure that innovation isn't stifled by too much fragmentation, but also that we foster healthy competition? It's a balancing act.
Energy efficiency is definitely a topic that's going to come up again and again as AI becomes even more pervasive. It's a foundational challenge not just for the hardware, but for the planet. And the balance between specialization and standardization, that's something worth keeping an eye on as these technologies mature. It sounds like the future of AI hardware isn't just about faster chips, but smarter chips designed with purpose and efficiency in mind.
Indeed, a truly exciting and complex frontier.
Well, that's all the time we have for AI Conversations today. Herman, thank you for breaking down such a complex topic into digestible insights.
My pleasure, Korn. Always a stimulating discussion.
And thank you for listening. Join us next time as we delve into more fascinating aspects of artificial intelligence. Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.